Today we're going to talk about graphing cube root functions. In a previous lesson we talked about the square root functions. A cube root function is a radical function with the index of a 3. The parent function for the family of cube root functions, f of x equals the cube root of x. So again, notice that index of a 3 for the cube root. Now, something that we haven't seen a lot of this year, we're going to see this time the domain and the range of this function are both all real numbers. And you can see that over in the graph. So if you notice, this is the graph of the parent cube root function right here. Notice this is showing a domain of all x's, so all real numbers for the x's. I see things with these arrows going on forever on the positive side and on the negative side. But I'm also seeing y values that would be going on forever. Now these are fading very, very slightly, but they would go on forever, just like these would keep dropping forever. So here's a situation where both the domain and the range are all real numbers. So the graph of f of x equals the cube root of 3 constantly increases during the entire domain. So again, thinking about it. So here, as the domain is increasing, notice how the s, or kind of sideways s, is kind of increasing at the same time. So as the domain increases, so isn't this parent function going this way. It's increasing on the y values as it goes. So just like we've seen in the other ones, we can transform graphs of cube root functions in the same way that we've been doing it for the square roots, the absolute values, for the quadratics, and for the exponentials. So like we did with the square root functions, as we've done with a lot of our functions this year, is we're going to draw a graph of h of x, which equals the cube root of x minus 4, and we're going to make a table. Okay, so like we talked about with the cube root functions, we want to have our domain very specific on what we're plugging in. So unlike the square root functions where we couldn't have negatives, we can have a negative that's done with a cube root, right? Remember, we could have negatives coming out. So we got to consider the negatives and the positives. So we also, though, want to consider, because we're looking at cube root, we want to think of our perfect cubes. So again, before we kind of get started, let's just kind of remind ourselves, what are our perfect cubes? So 0 would be one of them, 1 would be one of them, 8, because 2 times 2 times 2, 27, 3 times 3 times 3, 64, 4 times 4 times 4, and all of those also with their negatives, so negative 8, negative 27, negative 64. And it goes on, but we'll keep those numbers probably easiest for us to be able to graph. So let's look at our table. So with the function that we're talking about, I might plug in negative 8, because I want to see what's happening on the negative side as much as the positive side. I might plug in the negative 1 and the 0, and then the positive 1 and the positive 8. And again, because of those being perfect cubes. So as I plug these in, when negative 8 goes in, when I take the cube root, it's negative 2. And then when I subtract 4, I get negative 6. When negative 1 goes in, the cube root of negative 1 is negative 1, minus 4 is negative 5. When 0 goes in, negative 4 comes out. When 1 goes in, the cube root of 1 is 1, minus 4 is negative 3. And when 8 goes in, the cube root of 8 is 2, minus 2 is negative 2. So pause the video for a second, draw that graph, and then we'll come back and talk about how we compare that. Okay, so I didn't tell you my scale, so maybe we're going to be a little bit different from each other. But as you can see, this is the h of x. I went by 1s on my y-axis and 2s on my x-axis to make it work. So what I want you to notice is we have to still draw that smooth curve. It kind of looks a little bit linear in here, but it's still curving. Okay, so we want to do this little S kind of curve here. I also put in the parent function, f of x, which would look like this up top here, just so we can kind of get a feel for what is actually happening. But as we have probably started to figure out and saw right from the beginning, when I'm comparing the graphs, this -4 is doing that vertical translation, and the -4 outside of the radical is telling me to go down 4. So all of our points here are shifted down 4 units, and so that would tell me that h of x shifts down 4 compared to the parent function. So for example 2, what we're going to do is graph g of x and then compare it to the f of x parent function. And I'm going to I set my graph up this time with the 2's on both the x and the y. So here again, we want to be careful when we're setting up our table now. We want that radicand to become a perfect cube. So again, just quickly, maybe so we have it in our sights, 0, 1, 8, 27 would be some of the perfect cubes. Okay. Again, we kind of want to think about having these radicands, like we did on the previous one, show something that looks like this. But those aren't our x values. We want to make the radicand become those numbers. So how do I add 2 to a number that gives me the -8 that I want? Well, it would be -10. So that's the x value that's going to go in. Then the next one is a -1. Well, what plus 2 gives me -1? -3. So that's the x that I want to go in. -2 plus 2 gives me the 0. -1 plus 2 gives me the 1. And 6 plus 2 gives me the 8. Now, let's just get rid of these because this is now going to confuse us. But that's a way to kind of help figure out what is the domain that I'm going to be using. Okay, what are the x values? Now, I just have to use my order of operations. So when 10 does go in, I'm sorry, -10 goes in, I get -8. When I take the cube root, I get -2, but it's negative, so it's +2. When -3 goes in, it's a -1. The cube root is -1. -1 is a 1. -2 gives me 0, so that one's going to be at 0. -1 goes in, it's a 1. Now it's a -1. 6 goes in, it's an 8, which makes it a 2. Now it's a -2. All right. Then I just want to plot these points real quickly. So -10, 2. -3, 1, -2, 0, -1, -1, and 6, -2. And again, a nice smooth curve to show what g of x looks like. Okay, now compare that to the parent function. Well, a couple things happened on this one, right? So g of x got flipped, right, because it was going up the other way, and that's because of the negative number out front, and shifted 2 units left. Okay, so it got flipped upside down and it got shifted 2 units to the left. And remember, if somebody said, what is the domain and the range of this function? All of these are going to be all real numbers for the domain and all real numbers for the range. So on this next example, example 3, we're going to also graph. This one's got a lot more things happening to it, and so we're going to see what that looks like in a moment. And again, what I want to think about is, how do I create perfect squares? So the 0, the 1, the 8, the 27th. So like we did on the last one, let's just kind of write these off to the side. So I want to make a -8, a -1, a 1, and an 8. So what number minus 3 gives me a negative 8? Well, negative 5. What number minus 3 is negative 1? Well, that's a 2. What number minus 3 is 0? That would be a 3. What number minus 3 gives me 1? That would be 4. And what number minus 3 gives me an 8, which would be the 11. Okay, so again, we're using those perfect squares to try to help find the x's that we want. And I'm just going to get rid of those so we don't confuse ourselves again. Now we have a lot to kind of think about on this one. My order of operations. So negative 5 goes in. The inside becomes negative 8. The cube root is negative 2. Times 2 is negative 4. Plus 4 is 0. 2 goes in. It's now negative 1. The cube root is a negative 1. Times 2 is negative 2. Plus 4 is 2. 3 goes in. I get a 0. Times 2 is still 0. Then it's a 4. 4 goes in. It becomes a 1. Take the cube root of 1. It's a 1. Times 2 is 2. Plus 4 is 6. When 11 goes in, I get 8. Cube root of 8 is 2. Times 2 is 4. Plus 4 is 8. So now I can just plot those points. So negative 5, 0, right there. 2, 2 is right there. 3, 4, 4, 6, and 11, 8. 6, 8, 10, 11, 2, 4, 6 must be right there. Okay. Again, I draw a nice smooth curve following the kind of path here. And I would label this g of x. Now, what are the things that are happening? So g of x, compared to the parent function, it shifts 3 to the right this time. Up 4. And it was stretched by that number in the front. Because that number being bigger means that it's jumping by higher numbers, so it's kind of stretched. Okay, so that's how you would kind of use these tables, looking for those perfect squares, or now this section, perfect cube roots for the cube root functions, and finding the x that makes that perfect cube, and then being strong on your order of operations. Now, just like we saw in the square root functions, that's really what we're focusing on in this year's work. I'm not so concerned about the average rate of change that's on the next example, so we're going to stop there at example 3. If you have any kind of questions on the beginning parts of this, please make sure you ask so that we can make sure that you are all set, and we'll see you in class.